Okay, perfect. Hello, everybody. My name is Luis. I'm going to talk about the software implementation aspects of differential forms in the context of my bachelor thesis, which was developing a Rust implementation of finite element exterior calculus on coordinate-free simplicial complexes. So I am working with differential forms in the context of this framework of finite element exterior calculus, which is a combination of basically the finite element method with the exterior calculus of differential forms. And this means I'm developing a finite element library that is able to solve PDEs that are formulated using differential forms by tackling the weak variational form of PDEs. So the goals of my implementation were to embrace differential geometry as much as possible, meaning I have a library that should be able to solve PDEs on manifolds of arbitrary dimensions. I'm actually working with proper differential forms and not any vector proxies, so any rank differential forms. And as is typical for finite element exterior calculus, I'm able to treat manifolds with non-trivial topologies by doing a treatment of cohomology. The biggest specialty about my library is probably that I do geometry intrinsically using a Riemannian metric instead of any global coordinates. So our PDE is posed on some Riemannian manifold with some metric, and as I said, it can have a non-trivial domain, meaning we can have holes inside, just like for tori, and the Betti number, beta k, tells us the number of k-dimensional holes. We need to discretize our manifold, and we do this with a mesh, and we're using here Simplicial mesh, so a mesh that is made up of simplices, and we can obtain this by doing a triangulation of the manifold. And the simplices, we've seen these before in the lecture, so this is basically the idea of taking the convex hull of a set of vertices. These are now vertices with coordinates, and this is the definition of a coordinate simplex, and you can have points, line segments, and it's a generalization of these things, triangles, tetrahedrons, and so on. We then want to shed these coordinates, and we use coordinate-free abstract simplices instead. So for the before we had geometry, now there's no more geometry, and this is done by using vertex indices instead of vertex coordinates. So we number through, we have a global ordering of all the vertices in the mesh, and we just have lists of these vertex indices telling us which simplices we have. And this tells us the connectivity of the mesh, because we can now see which simplices share which vertices, and if they share them, they must be adjacent. And this then fully defines the topology without any geometry. We still have a notion of orientation, just like a triangle can be counterclockwise or clockwise. Here, any simplex also has two orientations, and these are the even and odd permutations of this vertex list. So the order of these vertex list matters. An important operator that exists in this context is the boundary operator. It allows us to compute the one-dimension lower simplices, which form the boundary of the simplex. So if we start with a tetrahedron, we can take its boundary and we obtain the faces of the tetrahedron, the triangles. The triangles themselves have, again, boundaries, which are edges, and the edges have vertices as a boundary. And this boundary operator also has a sign, which takes care of this relative orientation. If we now take all of the subsimplices and put them into one collection, this is then the simplicial complex. Just having the simplicial manifold with only the top-level simplices, so the cells, doesn't suffice, because we will have basis functions, finite element basis functions, living on the lower dimensional simplices. These are the degrees of freedom. Using the simplicial complex, we can also introduce the simplicial chain complex. This is a complex in the same sense as the de Rham complex is a co-chain complex. It fulfills a chain complex property, which is that the boundary operator applied twice is always 0. And we can now look at this boundary operator. So this is now the boundary operator extended to chains which are linear combination of simplices, so not only taking the boundary of a single simplex, but multiple, just like we have here formal linear combinations of simplices. And we can now do simplicial homology on this simplicial chain complex, which allows us to identify the holes of our domain. So basically forming the quotient group between the cycles and the boundaries of our simplicial chain complex allows us to figure out how many holes there are, which is the dimension of this cohomology group, a homology group. This boundary operator needs to be computationally represented, and here we just opt for a signed incidence matrix. So this just tells us if we have some low-dimensional simplex sigma I, it will have an entry in the incidence matrix of 1 if it is a subsimplex of the higher dimensional simplex sigma j. And the sign tells us the relative orientation of the two simplices. And otherwise we get 0. So this is the way we computationally represent this. So much for topology. Now we want to reintroduce the geometry by using a Riemannian metric. So this is basically just a function that varies over the manifold, where at each point we get an inner product on the tangent space, and this gives all of the geometry to our manifold. We can measure lengths, we can measure angles, and we can discretize this Riemannian metric at some particular point P by choosing a basis of the tangent space, which is usually induced by some chart map, and then just plugging this into this inner product, giving us a real number, which is the entry of this Gram matrix discretizing the inner product. The metric on the simplex specifically is constant because, well, triangles are flat, so there is no curvature, and the metric is therefore constant on the simplex. And the whole mesh then has a piecewise constant metric. We can, if we start with a coordinate simplex, which relies on some embedding, we can derive the metric on it by looking at the spanning vectors. The spanning vectors are, in the case of a triangle with 3 vertices, let's do V1, V2. These are the spanning vectors. So these are the vectors going out from V0. And these are vectors in Euclidean space. And now we can inherit this Euclidean geometry of the ambient space and use the Euclidean dot product to compute the entries of the metric tensor. If we don't start with coordinates, we can instead directly go from the edge lengths of the simplex. It turns out that the edge lengths are exactly equivalent geometric information to the metric. So these are coordinate independent for 2 vertices. We can always measure their distance. That's just a real number. And using some basic geometry, like the law of cosines, we can compute the entries of the metric based on the edge length, and also vice versa, go from the metric to the edge length. So these are basically equivalent. This finishes the definition of our mesh. We have a topology and a geometry, and now we can get to the differential forms. So instead of having differential forms on the continuous manifold, we now have differential forms on the simplicial complex, and these come basically in 2 flavors. One is simplicial cochains, which are the primary discrete objects we obtain if we take a continuous differential form and then we discretize it. But if we go the other way, if we have a simplicial cochain and want to reconstruct continuous differential forms, then we will always obtain Whitney forms. And these Whitney forms are basically the elements of our finite element space. So let's look at simplicial cochains. These are also the primary objects used in a different discretization framework, which is called discrete exterior calculus, which is kind of similar to finite element exterior calculus. So a simplicial cochain is basically nothing else than a real valued function on the simplices of the mesh. So a differential K form gets discretized into a K cochain. So values, real values for each K simplex in the mesh. And these are then basically just list of numbers in the implementation, and the interpretation of these numbers is best understood by looking at the discretization. So if we take a continuous differential form and make it into a simplicial cochain, all we do is we take the continuous differential form and integrate it over each k-simplex individually, always obtaining exactly one number for each k-simplex. These are the cochain values. Now we can derive what the discrete exterior derivative is. So we discretize the exterior derivative, and for this we have now an operator operating on simplicial cochains. And we start by looking at Stokes' theorem. And we write Stokes' theorem relating the exterior derivative with the boundary operator using a duality pairing, which just takes a differential form and integrates it over some chain. And then we can see that the exterior derivative is the adjoint of the boundary operator. And this inspires a natural discretization, where in the computational setting, the exterior derivative is also a matrix, which is the transpose of the signed incidence matrix that represented the boundary operator. And here we can appreciate how the exterior derivative is purely topological. There is no mention of the metric or any geometry. Now, the other side of the story are these Whitney forms. They are basically the finite element space of differential forms we're using. They're piecewise linear differential forms, which are, well, they're piecewise over the cells of the mesh. And they unify the different finite element spaces from vector calculus, like the Lagrangian finite element space, Nedelec elements, Ravier-Thomas, and discontinuous constant elements. These Whitney forms also form a complex, and they are a subcomplex of the full de Rham complex, where we have Sobolev spaces of differential forms. And this means that they are also a complex, they are subspaces, and they commute with the exterior derivative, meaning they capture the structure properly. It's a faithful discretization. We can do de Rham cohomology on these spaces. And now we're talking about closed forms and exact forms. And the existence of these forms also represents the topology. De Rham's theorem tells us that the cohomology here is the same as the simplicial homology. Now we also have a basis for this space of Whitney forms. And just like for cochains, we had one value for each simplex in each k-simplex in the mesh. In the same way, we have one basis function for each k-simplex in the mesh. And the local shape functions are just defined by some rule that generalizes to arbitrary dimensions involving the barycentric coordinate functions of the simplex we're on. And they fulfill a Whitney basis property, which is basically a generalization of the nodal Lagrangian basis property. We can look at some examples of these Whitney forms. Let's look at some Whitney 1 forms. They can be visualized using vector proxies, just as a vector field, and we look at them on the triangle. If we apply the rule we had, these are the three Whitney forms we get on the triangle, one for each edge, so edge 0, 1, 0, 2, and 1, 2. And if you visualize them, they look like this. So this is the reference triangle, and these are the Whitney forms on them. So 0, 1, this is the one for the edge down here, 0, 2 is the edge here, and 1, 2 is the edge like this. And we can now look at the global shape functions. Since an edge is adjacent to two cells, the support of the basis function is on both cells. And yes, these are the global shape functions associated with these red edges. And now we can do linear combinations of them to obtain fields like whole Whitney forms. We have a constant vector field, a purely divergent vector field. The errors are a little bit small. And a purely rotational vector field. Now let's solve a PDE using this. I'm not solving Maxwell's equations. I'm instead solving problems relating to the Hodge-Laplace operator. So this is just a generalization of the scalar Laplace operator. If you look in R3, basically it's a generalization of the scalar Laplacian and the vector Laplacian with different boundary conditions, and we can have this Laplacian at different places, as to say, on the de Rham complex, and it basically is defined using the exterior derivative and its codifferential. Now we need to transition to a weak variational form. For this, a crucial ingredient is to have an L2 inner product, and this is the L2 inner product for the differential forms. It is defined using this integral, which goes over the whole domain omega with respect to the metric volume form. And this initially confused me a bit because this is a different sense of integration. Normally you would integrate a K form over a K simplex, right? But this is an L2 inner product of them, so we always integrate over n-dimensional manifolds, even though these differential forms might have a different rank. And at each point, we just compute the pointwise inner product. And this defines in the Sobolev space, where the exterior derivative of the differential form is also square integrable. And now we can use our Hodge-Laplace source problem, which is just basically a generalization of a Poisson equation, by forming the inner product of del u with some test function v. And this is then a variational equation. This is actually not the form in which we want to discretize our problem. Instead, we want to use a mixed Hodge-Laplace problem, so introducing an auxiliary variable sigma representing the codifferential of u, and then we just replace the del u with the sigma. And now we got two equations, and this is mixed finite elements, this is called, and we also have the additional constraint that u should be orthogonal to harmonic forms. And if we now do once again we transition to the variational form, this is now the actual problem we're trying to discretize. And this is a problem that has been formulated such that existence and uniqueness is guaranteed for any f. If we now discretize this, what we need to do is we need to plug in basis expansions of sigma and u and tau and all the test functions into these bilinear forms, and then we can use the bilinearity pulling out the coefficients, and in the end we just have a basic linear systems involving matrices and vectors. And these sigma u and p, these are now cochains. These are the coefficients at the degrees of freedom, and we have here D, the discrete exterior derivative, as its matrix. And the other thing that appears here is this M matrix, this mass matrix, which is basically just a discretization of the L2 inner product on the basis Whitney functions. This can be so this is really the only Galerkin matrix we need to compute, and it can be explicitly analytically computed by just inserting the definitions of the Whitney forms, and then we can rearrange a bit, and this is the final expression. This is a constant term since the differentials of barycentric coordinate functions are constant, and this is the only this is the only integral we need to compute for which analytic formulas exist. Now let's look at one result I computed using my library. For this, I want to quickly talk about harmonic forms. So harmonic forms are concrete representatives of the cohomology group of differential forms. And so since they are isomorphic to the cohomology, there is basically more or less one harmonic form for each hole we have. So there's a whole linear span of them, but we can single out one. And we can basically compute these harmonic forms by just solving an eigenvalue problem, because harmonic forms, they are just elements that have 0 Laplacian, and this is just an eigenvalue problem where we set the eigenvalue to 0. And this is what I computed on the torus. The torus has 2 one-dimensional holes, the obvious one here in the middle, represented by this field, and one going around like this on the torus, and this is the other harmonic form. So these are the 2 harmonic forms that my library computed on the torus, and yeah, as I said, basically this example program I used for this, it can read in any mesh, in any dimension, and it can always compute these harmonic forms, irregardless of the topology. Really, the biggest problem is visualizing them. That's why I opted here for a simple 2-dimensional manifold that is embeddable in 3D. So, yeah. This is everything I wanted to say. Thank you for listening, and if you have any questions, feel free to ask. Yes.
Question. So you specified the local metric through edge length.
Yes.
Now, of course, there might be cases when the triangle inequality is violated, or even when you impose negative edge length.
Yes.
Which would then correspond to pseudometric.
Yes.
Have you tried computations where the metric conditions of the triangle inequalities and the positivity of edge length were violated?
No, I never did that because in my computations, I always started from an embedding and then derived the edge lengths from that, meaning the simplices are always coordinate realizable, meaning the edge lengths must always make sense and produce a positive definite metric. So, yeah.
It would be interesting to run your code, say, on Lorentz metric.
I mean, having the matrix from the embedding from the Euclidean metric
Yes.
of the Antian space.
Exactly.
And I think Ralph's comment goes in the direction, what happens if I put a much weirder Antian
Yes.
space? Yeah, where I do not have a positive definiteness, for example. Yeah, that well, there will be some difficulties. Yeah, it would be interesting.
Yes, for sure. I never tried it. Actually, probably a lot of features I've never explored because there's just such a big space of things you could try out.
You can solve the Hodge-Laplacian on a square,
Yes.
but with a Lorentz metric, so time-like and space-like edges.
Mm-hmm.
And then my prediction is then everything will blow up. Because the linear system will have a kernel or a near kernel.
Yes, yes. Makes
But
sense.
if the code is general enough, then it should be able
It should work,
at
yeah.
least to assemble the linear system.
Yeah, it should. That should work.
regardless of
I
stability.
agree. Yes. Yes. Any other questions?
Second question, yes,
Yeah.
concerns this example. Because when you compute the kernel of the Hodge-Laplacian, I would expect you get weird combinations of these two functions. Of course, the space spanned by the kernel vectors is always the same, but these two functions are very special.
Yes.
Did you get them by accident? Or
By accident. I computed
did you
it.
temper your code to get them?
No, that's what first try. This was first try actually, but I tried it on a lower resolution mesh, and then these vector fields were slightly slanted. They were still,
Combination.
yes, and so I guess it's just a coincidence that they're so neatly.
Okay, so you get the two cohomology generators from outside and inside.
Yeah. So I don't know, just by pure chance, I guess.
Actually, if you take these kind of nice generators, yeah, and then span the whole cohomology space by now as a group, by using n times the first one and n times the second one, it's like a coin design. Because then
Yes.
you get like a tilted thing, and then winding a copper wire
That's true.
around these torus, yeah, and the first coefficient is the tilt, yeah,
Yes.
and the second coefficient is how many layers this coil would have.
Yes.
And in principle,
I see,
one
interesting.
Could generate a technical coil, coil, yeah, in terms of such generators, yeah, and it's clear, yeah, that these are the nicest generators, and that smells like toroidal coordinates. These generators here. One could also have two in the first place.
Interesting. Okay, if there are no further questions, you can always come to me and still ask something.
But your code is general also in terms of dimension.
That's correct.
Of course, it will be very expensive to compute in 4 dimensions.
That's true, yeah. That's one of the biggest problems, that the computational complexity scales terrible with the dimension.